Hey you! Yes, you. You ever stopped for a second and thought, how exactly am I able to comprehend and understand these videos? You can only do that because the light from your device's screen reaches your eyes and the sound reaches your ears. Actually, almost every perception you have of the world around you is based on how that same light reaches your eyes and that same sound gets to your ears. And while it would have been so interesting to talk about the philosophical thought behind this notion, we're here to talk about physics. The physics that defines how sound travels around us and how light reaches us, whether that's from your screen 2 feet away or the sun 150 million kilometers away. Well, the answer lies in waves. Now, before we go on and on about waves making them sound like some weird abstract notion that you've never seen, like fruits, let's picture it. Imagine holding a slinky in your hand. Now, all you have to do is give it a gentle push and watch as the magic unfolds. Okay, I know it's not magical. Let me try to make this fun, okay? Let me try. God, you guys are such killjoys. Now, what you see here is basically what a wave looks like. As the coils in the slinky move back and forth, energy transfers across the slinky in a progressive wave. You can also see waves if you take a rope and okay, so I have no idea how else I can say this, but wiggle one end up and down. Anywho, a wave travels along the rope as you make these motions. And you've probably seen the same thing happen when you're spreading a cover on your mattress. It's the same motion, just a much cooler effect. In more complicated words, waves are a forward movement of energy through some form of vibrating back and forth motion. Think of how a group of sports fans can make the Mexican wave in a stadium, right? Where everybody is raising their hands and you can see the wave travel across the stand, right? But the spectators don't really move from their seats. They just move their hands up and down. And that's basically how waves are generated. The particles don't move, they oscillate back and forth and energy transfers. Let's take the example of a boy. Not the human homie kind of boy, but the kind that floats on the ocean's surface. Now, even though the ocean's surface has waves traveling across it, the buoy itself stays in place. This is because these waves are a result of the surface's motion up and down. They don't really need the surface to move with them. Waves are basically made because of periodic oscillations or vibrations of individual elements. And because it's periodic, the resulting waves follow a specific pattern. Still confused? Let's try again. A wave will have one individual particle moving to and from a central point called the equilibrium. As the particle reaches its maximum distance from the center point, we say the wave has reached its peak. And when it gets to the maximum distance in the other direction, we say that the wave has reached its trough. So it's basically just a constant back and forth movement between peaks and troughs. Now the maximum displacement from the equilibrium, that is the peak or the trough, is called the wave's amplitude. And this usually shows how much energy the wave is carrying. Waves with larger amplitudes usually have more energy than waves with smaller amplitudes. Now the distance between two peaks or two troughs is called the wave's wavelength. And you'll find that this is usually denoted by the symbol lambda and is basically just a measure of how long a wave is. And it's actually the reason why waves have different properties. There's a lot more to talk about here in wavelengths, but that comes later in a different chapter. For now, just think of wavelength as the difference between two wavefronts. Anywho, let's talk about frequency. In a sense, frequency is basically how many wavelengths or wavefronts cross a specific point every second. And we can calculate this by using f equals to 1 over t, where t is the time it takes for one wavelength to cross a point, also known as time period and measured in seconds. So for example, if a wave generated by an oscilloscope takes 6.4 milliseconds to complete a cycle, then in 1 second, we'll have 156 waves passing through any given point on the wave's path. So in other words, the wave's frequency will be 156 Hz. So, now that we know what a wave is and how it's measured, let's talk about how it's created and how many ways it can travel through space. Let's start with light. Now, light is an electromagnetic wave with a transverse pattern. What that means is that the wave has its peaks and troughs perpendicular to the direction of the movement of the wave. In other words, the individual elements or particles that push the wave move up and down while the wave moves left to right. Remember how you used a rope to make a wave? That's basically what a transverse wave looks like. The wave in the rope is moving horizontally, but the rope itself moves vertically. Sound, on the other hand, takes the form of longitudinal waves, and it is pronounced longitudinal waves, not longitudinal waves. It's long, not longe. What this means is that the individual particles move in the same direction as the wave. Let's take drums for example. When you hit the drum, its skin moves up and down, which makes regions of compression and decompression in the surrounding air. Now picture the air molecules rocking back and forth with the drum skin. This rocking creates a pressure wave that carries sound forward. This is actually pretty similar to how waves are made with a slinky. Remember, we did that too earlier? Anywho, the individual elements move between peaks and troughs in the same direction as the movement of the wave. Okay, we're done. Ha! No, of course we're not. We still got graphs to talk about. Remember? Regardless of whether a wave is transverse or longitudinal, we can always plot it with a displacement-time graph. So what this will do is it'll map the movement of any individual particle in a wave against time. And here's what that looks like. As the particle moves away from the equilibrium position and towards the crest, the graph maps it in the form of a rising curve against time. Then, as the particle moves back, the curve falls back to the center line too. Next, the particle moves away from the equilibrium and towards the trough. The graph maps this as a curve below the center y-axis, and then as the particle goes back, the graph goes back again. And this cycle repeats throughout the duration of the wave, or at least as long as you keep plotting it. And this whole process, it holds true regardless of whether the particle is moving perpendicular to the wave or in the same direction. Waves are everywhere around us, from the ripples in water to the songs we love. They all depend on waves. By understanding the concepts we've covered today, energy transfer, wave motion, transverse and longitudinal waves, and as always, graphs, you'll just see waves more. Make of that what you will. My work here is done. I'ma go get me some ice cream. See ya.